And today we're very pleased to have Dr. Sandeep Mudigonda to present his work on robust calibration of macroscopic traffic simulation models using stochastic collocation. And Dr. Mudigonda received his BS degree in civil engineering from the Indian Institute of Technology, Madras, Chennai, India in 2003. He graduated from the Rutgers University in 2006 with MS and in 2014 with PhD degrees in civil and environmental engineering. He worked as a postdoc at New York University in 2014. Recently, he's joined UTRC 2 in 2016 as a research associate. Dr. Mudigonda's research interests lie in simulation and calibration of large traffic simulation models, application of calibrating models to intelligent transportation systems, and transportation data visualization analysis. Without further ado, let's welcome Dr. Mudigonda.
Hello everybody, thank you Shah for the kind introduction. This work was performed as a part of my research thesis, my doctoral thesis, and also subsequently at my postdoctoral studies at NYU. And we presented this paper at the ISTTT that was held last year in Japan. So I'm going to start my presentation. As a first step to introduce the topic, for building accurate simulation models, we require primarily 3 steps. The first one is model verification. Second is the calibration, and then followed by validation. And all the 3 steps depend heavily on the availability of real-world data in order to get accurate and relevant predictions. So generally, to illustrate how the traffic simulation model looks like, we have inputs to the traffic simulation model, which are generally things like travel demand, geometry, operation rules, and so on. And then we have calibration parameters, which are usually dependent on user behavior or on the traffic characteristics. And then once we have these 2 inputs and calibration parameters, we obtain simulated output. And then basically the process of calibration involves comparing the simulated output with the observed output and trying to minimize the error between the simulated and observed outputs. Like I said, the model inputs generally involve driver characteristics, vehicle composition, travel data, and so on. Model parameters involve things like link capacity, speed limit, route choice behavior, and weather conditions, driver behavior data, and so on. The observed outputs usually involve flows and speeds, Q data, possibly then trajectories, and even if we try to simulate accident through surrogate measures and emissions and so on. Most of the earlier studies that were done in the for calibration were limited to either AM or PM peak periods, and usually the data involved much fewer number of days, due to which we cannot really capture the variability in traffic due to so many different conditions. As you can see in the picture below, So it could be dependent on demand, and supply. Some of them could be unexpected parameters such as incidents and so on. So obviously, if we want to cover all these conditions, we need to have data from a much larger sample. So the issues involved in calibration usually, to start with, we do not usually observe a typical day. So we cannot base our calibration on one single day, for example. So essentially, we are observing different types of variabilities in traffic flow. These variabilities could be from demands, they could be because of the supply, or they could be from incidents, work zones, or driver variability itself, or they could even be from unobserved phenomena. So in order to capture this variability, the ideal way is to have a stochastic traffic flow model. In this study, we use a stochastic first order traffic flow model. So as you can see, it's a partial differential equation in traffic density, and the density itself comes from a deterministic space-time domain and the stochastic domain, which captures different forms of variability. And the stochasticity further extends to the fundamental relationship with speed, free flow speed, and jam density as stochastic parameters, and also the inputs, which is in this case the demands could also be stochastic. Another important issue in calibration is, if we want to capture this variability, is computational effort. So just to highlight that, if you are considering a 2K factorial design with, let's say, n stochastic parameter inputs and two parameters with L and M distinct values, which capture the stochastic conditions, the number of replications that we need for this design would be M multiplied by L multiplied by 2 to the N. This is just for this for designing an experiment. But if we want to get statistically significant result, the number of replications for a level of precision gamma is shown by the equation here, where T is the T statistic for M minus 1 degrees of freedom and significance level of alpha. So the problem is, most studies which try to capture stochasticity use something like a Monte Carlo type of independent sampling, and the order of convergence when we use such methods is of the order of 1 to the square root of M, which could be computationally quite difficult to capture. So as an example, let's say if we are trying to simulate a free flow a freeway section with an on-ramp and an off-ramp. So in this case, we have 3 independent demands as inputs, and supposing that we are trying to have stochastic parameters, 2 of them, which are sampled at 10 points each, and let's say the standard deviation of demand is 140. So in order to achieve a precision of in traffic flow of 100 vehicles per hour at 90% level of confidence, the minimum number of replications needed is 8. So in order to capture all the variability from demand and the parameters, the number of runs that are required is 10 multiplied by 10 multiplied by 8 to the raised to the power of 3. So which comes to around 51,000 runs. And let's say even if each run takes 5 seconds, the computational time would be something like 71 hours, which obviously is very demanding. So just to show how the variation in number of runs is, you can see that in this chart with changing precision in flow and number of parameters. So it's very important to consider the computational effort when we're trying to capture the variability in traffic. So we propose a methodology which involves 3 steps. The first one is to capture the different conditions, which comes from the clustering process. The second is the stochastic collocation itself. And the third is parameter optimization. So I'm going to go through each one of them now. The first step is the clustering process. So in order to capture the variation in traffic flow, which could be from time of the day, weather, construction, and so on. So it could be from any of these conditions, and to capture the variations, we need to have a large amount of data. And in order to classify the variation into given set of groups, it's ideally the approach that's useful is clustering, which is essentially tries to minimize the variation within the group and also maximizing variance between the groups. So the premise is that similar conditions that are specific to a given cluster result in similar outputs, and similar parameters govern each specific cluster. So in this study, we try to use free flow speed to distinguish between on the supply side variation, and on the demand side variation we use the probability distribution of demand to capture the different conditions. So the distinguishable external conditions are captured using the clustering process. They could be from work zones, weather, and so on. The second step is the stochastic collocation. So the primary application of stochastic collocation is to overcome the computational burden because of using Monte Carlo-type of sampling. This is developed in the field of physics where it started to capture the variation in different types of partial differential equations. So the idea is when we have a infinite dimensional stochastic space represented by omega, so we reduce that space to an n-dimensional stochastic space, and this n-dimensional space is further discretized using Q collocation points. And finally, we try to interpolate the output at each of the collocation points and generate the final probability distribution of the simulated output. So in this case, the traffic density is our output, and the infinite dimensional space represented by omega is reduced to finite dimensional space, and then the finite dimensional space further is discretized using Q collocation points. Each of the point is represented by psi, and the final density at each of these points that's estimated as the output is interpolated using some interpolating basis polynomials. So in one-dimensional space, the interpolant is shown by U, that is shown on the right top corner. But when we try to expand to n-dimensional space, the problem we encounter is this turns into an n-dimensional tensor product. So the number of points that you actually sample will become exorbitant. So in order to reduce that problem, the approach proposed by many researchers in the recent past is using a sparse grid. In this case, we use a Smoljak n-dimensional sparse grid interpolant that you can see on the left, on the right side here, which tries to reduce the n-dimensional tensor product. So just to give as an example, if we consider an n-dimensional grid for the Smoljak sparse grid, the number of collocation points is 21 as compared to the full tensor grid, which requires about 1,000 points. So you can see the the magnitude of difference that the sparse grid can make. So once we construct the sparse grid, at each of the collocation point, we use the probability value from the inverse cumulative distribution of either the parameter or input to generate at the actual value of the parameter or input that's used in the simulation run. And from each simulation run, we generate the simulation output, and then we construct the output distribution using the sparse grid interpolant. So the convergence rate in this case is of the order of 1 over square root of q, and obviously since the number of points is much lesser as compared to a tensor grid, full tensor grid, the convergence rate is much faster. To show as an example, say we have free flow speed as one parameter, and let's say we have jam density. Then we generate this simulation, the collocation points that you can see in the grid here, and at each of the points we use the demand distribution to reduce the variance, and we do multiple replications of simulation. And finally, we use the output from each of these points to construct the final distribution of the simulated output. So the third the third aspect of the calibration is parameter optimization. So as I said before, using each realization of the parameter set and the discretized demand distribution, we generate the simulated output, and using the output from each of these points, we generate the either flow or density distribution using the interpolation methodology that I mentioned earlier. And we compare the simulated distribution with the output distribution, and we use a test statistic, something like a Kolmogorov-Smirnov test, to estimate the error between the simulated and output distribution. And the parameter optimization, in this case we use SPSA algorithm to minimize the error between the simulated and observed outputs. So to illustrate the proposed methodology, we use a first order stochastic macroscopic model on a 3-mile 3-lane section of the New Jersey Turnpike, which is this particular section is located near interchange 7. We discretize the space and time using a cell transmission model, and we discretize the stochastic space using the sparse grid approach. In this case, to capture the stochasticity in the parameters, we use a Gaussian distribution for free flow speed. So ultimately, the set of parameters for each cell in this case are the mean of free flow speed, the standard deviation of free flow speed, critical density, and jam density. In order to perform the actual calibration, we use the electronic toll collection data from the New Jersey Turnpike to capture the demand variation, and also the traffic sensor data for flow and speed. We have this data over 8 months from January to August in 2011. We use a smaller sample to perform the calibration, and we use the other parts of the data for validation purposes. So to set up the clustering process, we use the k-means clustering approach. So the first step is we set up a desired number of clusters, and then we group the speed data using we grouped actually this the speed data to minimize the variance within the group. And at the end of the clustering process, we measure the coefficient of variation for each of the cluster, and we check if the coefficient of variation is more than 0.25. Then we go back and increase the number of clusters, and we repeat this process until the coefficient of variation for each of the cluster is less than 0.25. So for the AMP, this process resulted in 2 clusters, cluster 1 and 2. Cluster 1, it turns out that the reason for cluster 1 is a long-term construction activity. And for each of the cluster, we generate the demand distribution using the electronic toll collection data. So we perform the calibration process using the proposed methodology, and we have the observed flow distribution at 2 cells among the 5 cells that I mentioned earlier for the cell transmission model. And the figure shows the distribution of flow for simulated and observed flows for cluster 1. For the AMP period, the Kolmogorov-Smirnov test showed that at the end of the calibration process was 0.09. And to highlight the importance of the proposed methodology, the proposed approach required just about 4,000 evaluations, whereas something like a Monte Carlo type of sampling would have required 180,000 runs. So that's a major advantage of the proposed methodology. The same result for the second cluster in the AMP period showed very similar results for the error statistic and also the number of runs required. In order to highlight the importance of using multiple days for calibration rather than one single day, what we did was we tried to do the calibration for the AMP period using only 1 day's data, and we compared the output flow distribution for using the proposed approach, which included 43 days of weekday data. This process resulted in an error test statistic of 0.25 using limited data, whereas using the proposed approach, the test statistics were 0.09 and 0.08. So obviously, another aspect of using multiple days of data is highlighted using this result. Another test that we did was to test to see the effectiveness of calibrating a model using only 1 set of global parameters rather than the 2 sets that we obtained for the AMP period. So the fixed, which we call the stochastic, fixed parameter model, where we do not cluster the data into different categories. And then we compared this approach with the varying parameter model, which is nothing but the proposed approach. And ultimately, we compared the speed, the flow predicted using each of these models for the PM peak period in July. So this is like a validation of each of these models for a different time period. So we use July for in the PM peak period Just to note, just like the AM peak period, we also perform the calibration for the PM peak period as well, using both the approaches. Excuse me. So this chart shows the difference between using a varying parameter model versus a fixed parameter model. So for a fixed parameter model, the KS test statistic resulted in a value of 0.29 versus the proposed approach, which had a KS test statistic of 0.08. So this result mainly highlights that there's a statistical difference between the result, the predicted result, when we use a varying parameter model versus when we use a fixed parameter model. So as a generic marker, what we could conclude is that if we see the output conditions which is diversely varying, if we have different outputs in which form different clusters, then ideally the calibration for such outputs would be using a varying parameter model. So to conclude, summarize and conclude, in order to capture accurately make predictions from traffic simulation models, we need to capture variations in the traffic from different conditions. So in order to capture this stochasticity, we need much larger sets of data. However, this large set of data poses the problem of computational effort. So we cannot ideally use a Monte Carlo type of sampling. So an important aspect of the proposed approach is to capture, is to reduce the computational effort that could result if we use a Monte Carlo type of sampling. So we propose an approach based on stochastic collocation, which uses a sparse grid interpolation approach. So we show that the sparse grid approach is much more efficient than a Monte Carlo type of exhaustive sampling. Also, ideally, if we want to parallelize this process of generating the interpolant, we could further reduce the time consumed in the calibration process. So we show that the proposed approach can be applied for various clusters in the AM and PM peak periods, and we obtain different sets of parameters for different conditions. So that highlights the importance of using the clustering approach to distinguish different conditions of traffic. We also show that the proposed methodology requires almost 80 to almost even 98% less number of runs as compared to Monte Carlo type of sampling. And we also highlight finally that we cannot use like a fixed parameter to capture all the different conditions, which if we actually try to do that, the predicted output is very different output. So the proposed methodology can actually have a bigger impact in case of microscopic models where we have more number of parameters. Also, ideally, it would be very infeasible to use a Monte Carlo type of sampling for so many different parameters. This is the next step in our research, is to capture
Hello, Sandeep.
use the proposed methodology for macroscopic simulation model. Shao, can you hear me?
I heard your voice was discontinued for a moment, but now it's good. It came back.
Okay. Do you want me to go back and
Okay, now your voice
were you able to hear
disappeared
all
again.
of the whole of the presentation?
Not really, actually. I just, your voice just went away at the last slides, probably were on the last couple of sentences. I think it'll be fine. People have already got your idea, but I hope, you know, the voice quality could be okay during the questions and answers.
Okay, sure. I'll make sure. Maybe my throat is very dry.
Oh, no, not your throat. You're fine. Maybe some connection issues. You never know. Could be the server side. But
Oh,
thank you. Yeah. Oh, not your fault at all. Don't worry. So I just want to thank you so much for your nice presentation, and it's a great piece of work. And I wonder from the audience, you know, you can unmute yourself right now. And if you have any questions, you can just speak out to all the audience. Just unmute yourself and you know, speak out your questions at this moment if you have any. Or if you want to take a moment to organize your words, you can use the chat box instead. And when you use the chat box, please make sure that you send the message to organizers and panelists only. Again, organizers and panelists only. So the system is a little bit awkward, and only you select that could everyone see your message. Okay, sure. So that'll be it. So I think we would like to entertain questions at this moment. Any questions? Okay, I think it's usually like you know, people would wait me to throw out some teaser and they're going to you know, give you better questions, I guess. So
I hope
Sandy,
they were able to hear me properly.
yeah, I think so. You know, if I can hear you properly, most of them should. Um, so it's an interesting work that you use the concept of a correlation to reduce the number of samples and overall reduce the computational burden. So actually, I saw in your case study you only considered one random variable, right? That was a free flow speed.
Right. We use the cell transmission model.
Mm-hmm.
So one of the variation we saw was the variation in the free flow speed. So that was the one of the stochastic parameters, and also we captured the demand distribution. So that's, you know, for the on-ramp, off-ramp, and mainline demands. So those are like three more stochastic parameters.
Okay, and I wonder, are these so you have more than one stochastic parameters? Are these parameters like correlated or completely independent?
The demands that we observed were independent demands for, you know, the mainline, on-ramp, and off-ramp demands. What we observed in our case study were not correlated. They were, I mean, what we found out was they were independent demands.
Yeah, because it's interesting. Usually, if one on-ramp is congested, then you know the off-ramp would be likely more congested. So I would, you know, I would think that there could be a possibility of having the demand magnitudes somehow positively correlated across different locations. Because you know, if yearly congestion happens together. So, but
Sure, right.
yeah, it might be right.
That's an interesting point. But yeah, like you said, like I said, in our case study, we didn't really, you know.
Let's, yeah, just maybe that's valid for your case study, but there could be also other you know, cases where parameters are correlated. But just suppose that these parameters are correlated, then would your method still be applicable?
So the idea is to capture the variation. So if, let's say, the the mainline demand is correlated to the off-ramp demand, so in order to capture the variation, we can actually for the congested time period where we observe the correlation, which obviously would be very closely correlated, for that time period we could actually use only one demand as like the stochastic parameter, and use the same stochasticity for the output as well. I mean for the off-ramp as well.
Yeah, so yeah, my question was if a correlation exists between random parameters, would the like collocation method that you used to still be applicable? Like, would you still be able to reduce the sampling points significantly by the collocation method?
Right. So like I said, so as an example, if we have a congested time period, the mainline demand would be correlated to, let's say, the off-ramp demand, right?
Mm-hmm.
And that correlation would be fairly close. So like, it's something like 80–90% correlation. So if those parameters are so closely correlated, we
Just
can actually
suppose
get rid
they're
of
not,
one.
yeah, they're not exactly absolutely correlated. They're not. Their correlation factor is not 1 or neither close to 1. But my question, I'm just curious. I'm just curious about method, collocation method. Would collocation method be able to handle correlated random parameters?
Right. So when we find the correlation, we could actually reduce the level of variation. So probably we can get rid of one of the parameters, so that way
Okay.
I would think, it could still be applicable.
All right. Okay. Thank you. You received another question from David Hill, and he's asking actually the journal paper. I think your paper is
Right.
published
I
in
think the
part.
journal paper is available online. I think you can. It's probably available for free, the download, right? I can
Yeah, depending on the
all the papers
database.
from the ISTTT conference are available online, if I'm not
Yeah,
mistaken.
he was asking what the title is.
It's
So
the same title as the presentation.
yeah, the same as I guess if you Google David, if you Google the title and Dr. Mudigonda's name, you'll be able to find it.
Yes, I'm sure. All right, thank you.
Any other questions? Okay, looks like good. So by the end, Sandeep, would you mind if you share the slides with us?
Yes, sure, I can do that.
Okay, sure. So you can send me the slides afterwards. And
Okay.
again, well, thank you so much for the nice presentation, and it looks great. And so we will pause 1 or 2 weeks, and then we'll resume that webinar series again. And thank all of you for your attendance again, and hope you have a great weekend. Thank you. Bye-bye.
Thank you very much. Bye-bye.
All right. Bye-bye.